Okay, let me provide you with a motivation why we need to learn the relational algebra. So let's assume we want to do some queries of the database system and specify what we want to get of the data from our database systems. We have an example in this page. Let's assume we plan to find all the people who earn more than $1 million and who pay tax in Tallahassee. We want to find all these kinds of people meeting our requirements and conditions. Let's assume we have all the data stored in our database system already, and we want to find this kind of people out. How can we do this? You may assume we probably can use some programming language like C++ or Java or Python, and we can get all the data, screening all the data we have, and find the ones matching our requirements and conditions, and to get them. I think it's a good idea, right? In certain sense. However, it can also be a very bad idea because this program can be very complicated and also inefficient. We have to go over all the data we have in our database systems for screening, right? So if it is not a good option, how can we do this? Probably we need to have some other high-level query language instead. We need to have some other language to help us. Therefore, we propose to have the theoretical language we can implement. It's called Relational Algebra. In this Relational Algebra will cover all the theoretical operators and procedures and functions we can use to do this kind of query for us. It serves as a foundation for the SQL to be implemented later and to be introduced in this class as well, in this course as well. So based on the Relational Algebra, we can further implement them into SQL, which is more like a practical and application language we can use and program in our database system. So you can see the relational algebra is very important. It is the theoretical foundation of SQL, and all the knowledge we cover in the relational algebra will be implemented in SQL. So therefore, if you learn this section very well, then the SQL should be very easy for you to use in your program, because you know the basic functions in SQL and why we need to write queries in a certain way, because this everything will be based on the relational algebra we cover in this section. In the relational algebra, it provides a basic set of operations on relations. It can provide some basic principles. We also introduce why and how to design these operations and combine them in different ways to help us to do queries. Therefore, in this section, we cover both the operators as well as how to use these operators to help us to write queries to work on the relations we have. And what is the algebra? We have learned different kinds of algebras before, right? And to answer this question, you need to know what is the mathematical system for algebra. Generally, the mathematical system of the algebra consisting of two main parts. The first part is operands. Operands denotes the variables or values from which the new values can be created and constructed. Besides operands, we also need to have operators in the algebra. They denote some symbols representing the procedures that can construct new values from a given value. Right. And we have learned different algebras before. We show some examples here. We have the elementary algebra, linear algebra, and Boolean algebra. And we can also compare them with each other to show what are the operands as well as what are the operators. In this page, I prepare a table for you. Right? So we have different algebra systems as shown in this column. And we also want to know what are the operands and what are the operators. Let me highlight this column first as well as this row. Right. So for the elementary algebra, what are the operands? The operands should be very easy, right? Should be very simple. The operands covers all the real numbers, right? Some examples include like the natural number, right? 1, 2, 3, as well as some float number, right? Not 0.01, 101. These are just some examples. So the operands are all the real numbers we have. Then what are the operators? We have some basic operators. We have plus, minus, times, and division, right? These are the basic operators we can use to define. Well, of course, we can operators we can use in the elementary algebra, right? And based on that, we can define more complex operators, right? We can have this square, right? We can even have a cube and eccentric. So these four are the basic operators. And we can highlight them. And based on them, we can define more complex operators. This is the elementary algebra. How about the linear algebra? Linear algebra will work on the vector space, right? In other words, the operands we have will be some vectors, right? So we can represent these vectors as like R. R denotes a real number domain, right? We can denote R to the n denotes a vector of length of dimension n times 1, right? It is a vector. We can also have some operands which are the matrix, right? We can have R to the n times m, right? It denotes a matrix. The dimension is n times m, right? We can also have some even higher way operand like tensors, if you have heard about this, right? We can have like R to the n times m times l, right? There are even higher way tensors, or we can even times more, right? We didn't show here. We can even have some tensors, right? Right. And for the linear algebra, what are the operators? The operator we have can include like the inner product, right? And we can also have the outer product, right? We can also times this matrix with the vectors, right? Multiply, right? We can also have more complex product operators like entry-wise product, right? And eccentric. So these are the operators we can use for the linear algebra. How about Boolean algebra? What are the operands? So for the Boolean algebra, we are working on some Boolean values, right? They can be either true or false. So there are two basic values we can operate on in the Boolean algebra. How about the operators? For the Boolean algebra, the operator we can use include like a and, right? Or, and we can also have a not, right? And based on them, we can define more complex operators like XOR and etc. So these are the operators we can use for the Boolean algebra. Then let's come to the relational algebra. What are the operands? If you still remember the diagram I show here, right? Everything will be based on relations. That's the reason why we translate the diagram into relations. The relation will be the only foundation or only basis for the remaining sections. Therefore, for the operands we have for the relational algebra, we only have one single operand. It will be the relation. And how about the operators? For the relational algebra, we can define some basic operators, which include the union and difference. These are two basic set operators. Besides this, we also have selection, projection, and product, as well as renaming. So these are the basic operators we can use for the relational algebra. We will introduce them one by one in the following lectures. And based on these basic operators, we can derive more complex operators. I can highlight they are the basic operators. I can use a different color. Besides that, we can also derive more complex operators by combining them together in different ways, right? We can have different derived operators, something like intersection, complement, now joins. The join, we have different kinds of joins, like natural join, equijoin, zeta join, and semi-join. And extension, we have lots of joins. So these are the basic operators, and these are the derived complex operators by combining these basic operators. Okay, so this is a comparison between or among different algebra systems we have learned already. You have learned these basic algebra systems before, right? And in this course, we will focus on the relational algebra. It is based on the relations, and we will cover different operators we can use to operate on the relations to help us to correlate on the relation we have.